your Friday work. Again, we're working with still our same elastic potential energy equation, so I'll just rewrite that up top. That is 1/2 k x squared, where this k value is still a spring constant, and x is our displacement, and this tells us the elastic potential energy stored in a spring if we compress or stretch it. So in our simulation, I'm going to come over here first. We're still in the Hooke's Law simulation, and I'm going to go back into our energy simulation, the same one that you guys use on Thursday. And let's reset this just as a reminder. It's important to click all of these boxes over on the right side. It just gives us as much information as possible, and especially these values. That way it saves some of the calculations that we have to do. If I want to know how much energy is stored in this spring, I can just look up here at this elastic potential energy little bar graph, and right now it's telling me that I have 32.4 joules of energy contained, stored within this spring now that we've stretched it to 0.805 meters, and we've got a spring constant of 100 newtons per meter. So the first thing that you guys have to do in today's work is look at and sort of investigate whether the direction that we sort of move this spring in is going to affect the energy. Or basically, if I stretch this to 0.5 meters or whatever it is, will that give me a different energy than if I compress it 0.5 meters? And so that's the question that you're answering first. And basically, to do that, I set up a table in the first problem for sort of basically a stretch length and elastic potential energy. And then one of those is going to be, like, let's say -1 meter and +1 meter. And then you can use the simulation in both cases to figure out what your elastic potential energy is in each case. And then if I get, let's say I got 10 joules for each, right, then it seems like, okay, maybe the direction of that compression or stretch doesn't matter. If I got two different answers for that, then it would look like I would say, yes, the direction matters. Whether I stretch or compress maybe does matter, but that's what you are trying to figure out using a data table that looks just like that or similar to that in those first two problems. The second problem is just asking you to explain your trend. Now the second sort of experiment that you're running today is going to be sort of similar, but we won't be worrying about direction. Instead, we're just going to be looking at, for some value of k, which is going to be held constant, and then a bunch of displacement values or sort of stretch length values. We're looking to see how that affects elastic potential energy. So the first thing you'll have is a table that looks sort of like this, and the k value will always be the same. I don't remember what I picked for now. I'm just going to leave it at the 100 that I have just as the default in this simulation. And then I give a bunch of values of displacements. Let's say I picked 0.3, 0.5, 0.7, and 0.9 or something. And then for each of those values of your spring constant as well as your displacement, I could just come over to the simulation. Right now, spring constant of 100 newtons per meter, a displacement of 0.3. So I'll set that displacement over here. And then right now I'm looking, and I come up here to the potential energy, and there are 4.5 joules of energy stored within the spring as long as these two conditions are met. And so I could do the same thing for 0.5 meters and 0.7 and 0.9 meters, and I could record all of those things just in my table. And that's what the sort of first part of that second experiment is. Once you have your data table, I would recommend possibly screenshotting that, taking a picture, or jotting it down on a piece of paper or in a notebook or something, somewhere that will make it easier for you to access it. Because when we get to the last question for the day, I'm going to ask you guys to graph those results. And so I give a big blank graph like this, where we have displacement in meters on the x-axis, and then our EPE, our elastic potential energy measured in joules, on the y, and I'm asking you to basically put whatever your points look like, and then connect them as a line graph to show some kind of trend, hopefully or possibly, in your data. So it's important that you keep those data points on you because they'll correspond exactly to the data that you collected. So for what my data table looked like, it was like 0.3, 0.5, 0.7, and 0.9. And then I would just want to make sure that I put whatever energies that I found right there. So just based on what I have here, I forget what that was for the 0.3 meter displacement, but the energy should be whatever I got there. So I would graph up to this 4.5, it looks like. And you don't have to write the numbers on there, but you'll use whatever numbers are directly on that graph. So those are the trends that you're trying to pick out today as you apply that elastic potential energy equation.